Hi Lena, welcome on board this session. The topic of this session is Sideslip. This particular topic is entitled to the subject flight mechanics, and the target audience for this session are GATE aerospace aspirants, aeronautical, and aerospace engineering students. We are following the GATE aerospace engineering syllabus for flight mechanics, and we are focusing on this particular topic for this session. In the previous session, we did know about angle of attack. In this session, we will be first knowing about the definition of slip, and then we will be further moving on to the types of slip. We will also be focusing on side slip because this is a major point of interest for this session. We will be knowing few aspects of side slip angle, and further we will also be known about physical significance of the side slip and the methods of calculation and measurement of side slip. So before getting to know about a side slip, we should know about slip. So what is a slip basically? Slip is nothing but an aerodynamic state where an aircraft is moving somewhat sideways as well as in forward direction relative to the oncoming airflow or wind. So this kind of motion of aircraft is known as uncoordinated flight. So here we can see the relative wind indicated in blue color, and the aircraft longitudinal axis is tilted some way different from the relative wind, and the angle that is between these both are known as side slip angle. Now talking about the types of slip, there are two major types of slip. One is a forward slip and the second is a side slip. The forward slip and side slip are basically the maneuvers which are performed by pilots in order to compensate this relative winds change. So here, forward slip is basically used to reduce the height or altitude of an aircraft or airplane, which we are concerned about, and side slip is used to move the aircraft sideways. So when we are talking about side slip, it can be further classified into two subcategories. There are two methodologies which are being handled. The first one is the crab method, and the second one is the wing low method. Now we will be getting about the major focus of this session, the side slip. So what is side slip and what is a side slip angle? So side slip angle is basically nothing but the angle between the relative wind V infinity and the projection of aircraft longitudinal axis. So this angular deflection between these two is known as the relative wind, and longitudinal axis is known as the side slip angle. So basically we can see the side slip angle is denoted by beta, and for a coordinated flight the side slip angle must be zero, that is the aircraft must be aligned with the relative velocity or relative wind. So what is this relative wind which we are talking about so conveniently? Relative wind is nothing but let us consider that we are having a headwind. Normally we will be having headwind, that is if the aircraft is flying in this direction, consider this as straight, and there is some wind which is it is experiencing on its nose or on its face. So here we can see this is wind is acting in the opposite direction to the flight path. So consider the aircraft is flying in this direction, and there is a wind in the opposite direction which it is experiencing. It is similar to the wind which we are experiencing while riding a bike. So it's okay in this condition. This is normal condition, coordinated flight. But consider there is an alternate condition, as the atmosphere it isn't constant or static, so there may be differences. So here let us think that there is a crosswind at some particular location. That is, the wind is coming in this direction. So what is a relative wind based on these both? So the aircraft is experiencing both the headwind and the crosswind. So the relative wind is nothing but the average of the relative headwind and the relative crosswind. So here we can see the graph. It is a straight line and it is an average of these both. This is what the relative wind is. So when we are talking about side slip angle, we did see that there is an angular deflection. So here there are two possibilities. The uh, relative wind can be either from this direction or this direction, based on which we are classifying it as positive and negative side slip angle. So when the relative wind is from the right side of aircraft's nose, it is known as the positive side slip angle and denoted by positive beta. And when it is from the left side of aircraft's nose, it is negative side slip angle and it is denoted by negative beta. Now, what do we do to compensate this side slip angle? So basically, what we do is we tilt the aircraft into compensating the side slip angle. So here we can see the relative wind is in that this direction. So we will be tilting it and this direction, and here the relative wind is in left, and we will be tilting it in this direction. So this is basically how the side slip angle is compensated. So when the aircraft is tilted, the aircraft will be oriented towards the side slip angle or relative wind, and the aircraft will still be moving in this direction. This is evident in crosswind landings. Now let's see how an aircraft flies during a side slip angle. This is a short animation. The here So here we can see the aircraft was tilted towards the relative wind. Still, the aircraft was moving in this direction. So this is the relative wind, and here we can see these moments are also in some particular positive and negative notations. So basically, from flight mechanics denotion or notations, the way which we follow is that a clockwise tilt or the right wing going back, which is easy to remember, is a positive yawing moment. So yawing moment is denoted by n, and the anti-clockwise tilt or moment, or in which case the left wing going back, is known as a negative yawing moment. So this is how we compensate the side slip angle by using the restoring yawing moments. What is the physical significance of this side slip, and why do pilots perform it? As I said, it is majorly used for crosswind landings. You can see in some footages, the aircraft is landing at some particular angle instead of landing straight away to the runway. So here in crosswind conditions, that is here we see a crosswind coming by, and in such conditions the pilot is required to fly at a side slip angle in order to maintain the alignment with the runway. So if the pilot doesn't induce the side slip angle and compensate it with the yawing moment, what happens is that, consider this is the case, and if aircraft isn't generating the yawing moment, restoring yawing moment, the aircraft will be drifted off the runway. So the runway, as we know, is limited. So we have to land between this particular width, and if it isn't compensating, then the aircraft gets drifted off the runway. So this is an intentional situation. So we need to avoid it. So that is why pilots basically use the side slip angle and restoring yawing moment to align with the relative wind. So here we can see the relative wind. So this is the relative wind. We have a head-on wind over here, and we have a crosswind over here. So when we take an average of it, we get a relative wind. So this is the V infinity, which is denoted over here. So here we can see the pilot is basically aligning with the relative wind and his landing. And two different methods are used over here. Either it is an grab method where the aircraft totally orients in this direction and also lands in this particular orientation. So this is known as the grab method. So the motion is basically representing the crab's walk or crab's motion. But this is normally not preferred, as when an aircraft lands like this, the aircraft may damage its landing gear, or some conditions may also cause accidents. That is, the aircraft will be totally tilted over. that is in preferred. So when an aircraft approaches near the runway, the aircraft, as soon as it is near a particular critical point, the aircraft performs a maneuver where it restores all the action by tilting the aircraft and aligning the nose along with the center line, runway center line. So the next method is the wing low method, where the wing uh, which is related to the wind. So here this wing is related to the wind. So this particular wing is tilted or rolled towards the wind. So the aircraft will be flying somewhat like this, not straight. So here in crab method, the aircraft wing are basically maintained in straight level. Consider this as an aircraft, and in crab method it is straight, but in a wing low method it isn't straight and it is tilted towards the relative wind. Now, how do we calculate the side slope angle? This is an angle basically. So, how do we calculate it? Before calculating it, we need to know or basically establish a basic three-dimensional view and notations of this case. Let us consider that an aircraft is in flight, and there are three velocities of an aircraft. That is, let us consider this is an x direction, this is the y direction, and this is the z direction or axis. Now, the velocity along the x-axis, so aircraft will be moving like this. So this velocity along the x-axis is u, and the velocity. So there may be some motion towards the y-axis too. So aircraft is moving like this. How do you denote it? That is why it is having some x direction movement. It is having some y direction movement. So this is the y direction movement, this much amount, and it may also have some z direction movement, so that is up or down. Aircraft may be moving up or down. So this z direction, the velocity in z direction is denoted by w. So these are known as the components of velocity. So the velocity components are u, v, and w. So this is three-dimensional isometric view. Now, when we consider a rectangular cuboid box around it, so here we can see this is a rectangular cuboid box. We cannot be calculating on these three velocity components. Instead, we will be having a resultant velocity, which is caused as a resultant of these three velocity components. So we are taking a component of velocity v. So this velocity is the velocity of the aircraft, not the wind. So here the resultant velocity is nothing but the by applying the Pythagoras theorem, we are obtaining it. So here v square is equal to u square plus v square plus w square. We need v, so we are taking the square term over here, which will be turning into square root. We can see that now there are two angles which are being formed. So there is some angular deflection with the u. Uh, so this is the angular deflection between u, and there is also an angular deflection between v and w. So this angular deflection between u and v, the resultant velocity, is known as beta, and the angular deflection between v and w is known as alpha. So it is better understood if we are taking the top plane. So here beta is shown, the angular deflection between u and b. This is what we see when from top of an aircraft. So when we are seeing sideways, so this three-dimensional deflection isn't particularly shown. So we are seeing a two-dimensional object. So the deflection difference between u and v. So here we can see this angular deflection in three-dimensional space. This is known as the angle of attack. We can see these are angles, basically angles. So can we introduce the basic trigonometry and find out the angles, so the beta and the alpha. Is there a possibility? Let's see. So here, the basic thing which we are seeing is the angle. So this is the beta. This is an angle. Don't see it as side slip or alpha angle of attack, not these complex terms. Just take it to the trigonometry. So what we know from trigonometry is that we know that if there is an angle, and if we know the length of the opposite side or height of the opposite side, and the hypotenuse, the length of the hypotenuse, we can obtain the angle, what is it is. So here we are interested to calculate the beta angle of it. So sine theta, from trigonometry formula, sine theta we know that is the ratio of opposite side. So this is the opposite side, and the hypotenuse. So this is the hypotenuse. So this is the hypotenuse, and this is the opposite side. If we know the values of these both, we can easily find out the beta. That's what we have done. Instead of theta, we are taking beta, and instead of opposite side, we see that opposite is nothing but the v, the velocity component in y direction, y axis. So here we are taking small v, this is small v, and hypotenuse is nothing but the resultant velocity. So resultant velocity is taken as capital V. So this is the basic difference. And as we said, resultant velocity is nothing but the u square plus v square plus w square and square root of it, which is obtained from the Pythagoras theorem. Okay, uh, Pythagoras theorem. And we are particularly concerned about this beta, so we are taking it to the right hand side, which will be turning into an inverse. Now, similarly, we can also find out the angle of attack or alpha. So, if we know the adjacent and opposite side, so this is the adjacent side and this is the opposite side. So, in this case, we know these both. So, if we apply the formula of tan theta, that is opposite by adjacent, we can easily find out the angle of attack alpha. So similarly, if we take the tan on to the right hand side, it will be turning into tan inverse. So here the adjacent is opposite is W. This is same as this W, and the adjacent is U. Okay, this. So this is what we get. Okay, here we have these two formulas. What about the case with reality? So in real case, the aircraft might not be totally tilted like this and moving in a direction like this. This is unrealistic. So we need to consider or restrict the case to real case scenario. In real case scenario, mostly the side slip angle and angle of attack is lesser than 15 degrees. Why is it? So basically, we did see in the previous session that angle of attack is a major factor for deciding the stall. So if the angle is higher, the aircraft or wing would stall. So this angle may not exceed 15 degrees for conventional aircrafts. So for this case, if the side slip and the angle of attack are smaller than 15 degrees, then the tan theta, tan inverse and sine inverse can be neglected, as the resultant value would be very small. The change would be very small. Consider that if you are obtaining with sine inverse, the answer is somewhat like 0.024, and the answer with without sign will be 0.02. That's it. That is the change which we'll be seeing. So here we also need to know that we have calculated the alpha and beta values, but these two alpha and beta values are in radians. We did see about conversion of radians to degrees and degrees to radians in the previous session. Now, how do we measure this side slip in real case? In basic gliders, we can see a yaw string. Yaw string is basically shown to see the difference between yaw, but it can also be used to measure the side slip. So here we have an headwind, so it is in straight direction. This is nothing but a string which is taped to the canopy of the glider. So we when we have a headwind, the yaw string is straight. So when we have a crosswind coming from this direction, there will be some relative wind, and this relative wind will be acting so that the yaw string will be tilted to this direction. In modern aircraft, we use turn and slip indicators. Still, this modernization is limited to 80s or 90s. Today's aircrafts do not use these kind of instruments. Instead, they are digital. But as far as small aircrafts are concerned, they basically still use these instruments such as the Cessna and other kinds of small aircrafts. This is a turn and slip indicator. When an aircraft turns, it also detects the turn. So this is the left turn and this is the right turn. Additionally, there is a slip indicator. So this is nothing but level gauge, the bobble gauge. Here we can see that this center black dot tilts to the left or right side based on the slip. So if the aircraft slips to the left side, the bob will be tilting to this direction. And if the aircraft is slipping to the right side, the bob will be tilting to this direction. This is known as the slip indicator. This is basically associated with turn indicator too. That's why this instrument is known as turn and slip indicator. I always recommend you to go through the book content so that you will obtain a broad knowledge about it. So, as far as book reference is concerned, you can go through the Flight Stability and Automatic Control, the second edition of it, by Robert C. Nelson. In the particular page numbers which deal with this particular topic is 21 and 30. So this is restricted to the second edition. You can always find this book in your college library or some other resources. And additionally, for obtaining or gaining knowledge, better knowledge about these kind of practical things, you can always see it from a pilot's perspective. And the book which I recommend for this kind of pilot's perspective, so this is a pilot's guidelines provided to the FAA, which is free to download from the FAA Federal Aviation Administration's website, faa.gov.in, so or AC something. So here we can .com actually. So here the pilot's handbook of aeronautical knowledge, the 2016 edition. The chapter 5 deals with this the aerodynamics of flight. And the particular section number is 5 to 18, and the page number which deal with these are 117, 524. That's it. We have reached the summary of the session. We did know about the side slip, and we also did see the few calculation and determination methods of side slip angle. That's it for this session. Thank you. Let's crack Gate Aerospace Engineering.